a little tutorial to give a tour through what's called the HR diagram. So this is the Hertzsprung-Russell diagram. This is the main picture astronomers think in terms of stars, what they're doing, and what their properties are. So when people first started plotting stars, you could think of it plotting their how bright they are versus what color they are. People first realized then that stars are not just randomly spread out in that brightness versus color space. They have regular patterns, and most all stars in the sky are going to fall along a line, which is the main sequence, and then other stars that were off the main sequence again followed patterns, either being stars that we refer to as like the red giants, or the remnants left over after a star has died, white dwarfs. So there are different ways of plotting things in a HR diagram. So the most straightforward way of thinking about it, and this is the way your book mostly talks about it, you have the luminosity of the star relative to the luminosity of the sun. So one solar mass star is along that coordinate of 1. And it is luminosity versus temperature, but temperature goes backwards. So the coolest stars are over on the right, and the hottest stars in the sky are along the left or towards the left. So red stars are to the right, blue stars are to the left. Okay, instead of temperature, you could just have a spectral type for the star, and the spectral type is telling you the temperature. So we could also have an HR diagram of luminosity versus spectral type, and stars will fall into the same pattern. And if instead of knowing the luminosity, what we have is the absolute magnitude, then you could make an HR diagram out of absolute magnitude versus temperature, or absolute magnitude versus spectral type. We're not too concerned about absolute magnitude in this class because trying to avoid logarithms, and I think it's just sort of unnecessarily complicated. But the idea behind magnitudes go back to ancient Greek astronomers who introduced magnitude classes for stars. Like, these stars were of the first magnitude, the brightest in the sky, and then the next brightest group of stars were the second magnitude stars, and on through to the, say, 5th magnitude stars, being the faintest the eyes could detect. Well, it turns out that the human eye has a logarithmic response to input, and so when you're spacing them evenly in magnitude, in terms of luminosity, you're actually spacing them logarithmically. So it's not all that important for the class, but just know that a smaller absolute magnitude is going to correspond to a brighter star. So we actually have objects in the sky with negative absolute magnitudes. Those would be brighter than anything with 0 or a positive absolute magnitude. All right, what are the spectral type, temperature, absolute magnitude number, and luminosity of star A? So this is just an exercise. We're going to go around the horn here and read off what its coordinates are on all those different axes. So spectral type of star A, it is a B type. Reading off the top axis. Its temperature, this is logarithmically spaced, so I don't really care so much that you get it spot on. I'm just going to call it roughly about 15,000 Kelvin. Absolute magnitude, it's a 0. Reading off the right axis. And then luminosity is 100 solar luminosities. So star A is intrinsically 100 times more luminous than our own sun. All right, which 2 pairs of stars labeled A through G in the diagram have the same temperature? Well, if we look on the axis at the bottom of the figure, Stars B and C have very different luminosity, but they are both hot. So one pair is B and C. Another pair that have identical temperatures, be E and D. Do stars of the same temperature have the same spectral type? Yes. So stars B and C are both B spectral type. Star D and star E are both F spectral type stars. Which two pairs of labeled stars have the same luminosity? So now we're reading off from the vertical axis on the left. Along that, star G and star A have the same luminosity, and star C and star F have the same luminosity. Do stars with the same luminosity have the same absolute magnitude number? Yes. So for example, for A and G, those are both corresponding to about 0. If stars have the same absolute magnitude numbers, do they necessarily have the same temperature? Use a pair of stars from the HR diagram of the previous page to support your answer. So do stars of the same absolute magnitude have the same temperature? And no, they do not. If we look at star A is B spectral type, around 15,000 Kelvin. Star G, much cooler, around 2,000 Kelvin. Stars of the same spectral type have the same temperature. Those are axes that are opposite each other. Stars that have the same absolute magnitude number have the same luminosity. Those vertical axes are opposite each other and match up 1 to 1. All right. For each of the following star descriptions, state whether this star would be a red giant, white dwarf, or main sequence star. Provide the letters of a star from the HR diagram that fits each description. We want a star that is very bright, so high luminosity, and very hot, so a high temperature. So we're looking for a star that is in the upper left-hand corner of the HR diagram. So we could pick star B. It's very luminous and very hot, and that is a main sequence star. We want a star that is very dim and cool. So we want low luminosity, low temperature. So we're looking for a star in the bottom right part of the HR diagram. So we could pick star F, and that star is also on the main sequence. That's a low mass star. We want a star that is very dim and very hot. So very dim is towards the bottom and very hot is towards the left. So we're looking at the bottom left quadrant. You're in the regime of the white dwarfs, and that is going to be star C. It is a hot star, but it's not very bright because it's very small. White dwarfs are typically Earth-sized, not Sun-sized. All right, last one, we want a star that is very bright and cool. So high luminosity, upper part of the diagram, low temperature, right side. So you want a star that is cool and bright. And that's going to give us a star that is a red giant. So for example, we could pick star D another star G. Let's pick G. It has a low surface temperature, but a high luminosity. That's because it's a very big star, hence the giant in the name.